Good morning. So, today I will continue with further discussion on thermoelectric material and thermoelectric generator devices. So, what we have seen in the previous lecture related to thermoelectric material and thermoelectric generator is that what is the fundamental the idea of thermoelectricity, which had started long back, and it is started after the discovery of Seebeck, followed by Peltier and Thomson, and then what we have seen in the recent days, people again started working on thermoelectric generator, that means to make energy devices out of that concept which was given long back by Seebeck and Peltier and Johnson and their co-workers. So, the reason is that we have lot of wastage of heat, and due to this wastage of heat, a large portion of energy is not being used, and we know that thermoelectricity or thermoelectric effect is a phenomenon by which one can convert heat energy to electrical energy. So, as it was given by Seebeck that if you make a thermocouple and you keep two junctions of a thermocouple at two different temperature, then because of this temperature difference, an EMF will be generated, and this EMF is known as thermo EMF. So, it is a conversion of heat to the electricity. But now in the naturally whatever the heat for whatever sources they are getting lost, they can be used properly, and if we can make a good thermoelectric generator or thermoelectric devices based on the simple Seebeck effect. So, just what we have mentioned that even these automobiles which are regular use, every day there are a lot of wastage of heat. Okay. So, when we drive a car, we understand that there are a lot of wastage of heat which are not being used, and we use some battery inside the car to give power to the different appliances which are being used in the automobile. But if we can use that heat energy which is being lost and convert it into electrical power, we can give power to these appliances without a battery inside the car, and that is possible when we have this thermoelectric generator. And then what we have seen that in order to make thermoelectric generator, one need to do lot of research the material, because there are very important physical properties and also many parameters which are useful to be optimized before we make a proper thermoelectric generator or thermoelectric device for real use. So, one of the factor is like figure of merit, another is power factor. Okay. So, some more basic physical quantities like Seebeck coefficient, electrical conductivity, thermal conductivity, which should be studied in detail when we try to design a thermoelectric generator based with a particular material. Okay. And then what we have seen out of broad classification of materials like metal, semiconductor and insulator, semiconductor seems to be a better material in performance as far as thermoelectric generator is concerned. And then there are many other materials, a plethora of materials have been studied as thermoelectric material. considering to optimize the power factor or the figure of merit, which eventually gives higher efficiency of a thermoelectric generator, higher power output of a thermoelectric generator. So, we looked into all these aspects in detail in the previous lectures, and today I will just discuss some questions to review this chapter and to understand again everything whatever we have studied in the previous lectures. Okay. So, let us look at the first question. What is the typical waste heat percentage from different energy sources? So, we know that we are surrounded by many energy sources, particularly the sources which give us electrical energy. So, if you look at different energy sources, okay, like let me start with the simple automobile. Okay, this is something which gives us the energy in that sense that we drive car. Okay. So, it gives kinetic energy. Okay. We have factory, we have the nuclear power plants, we have thermal power plants, etc. Okay. So, if we look at all these energy resources or the waste heat producers, then and make a percentage of that, what we can notice that almost 66% of heat energy is getting wasted, okay, and closely 34% energy is under use. All right. So, now the question is, can we convert this to electrical energy? And the thermoelectrics is the the energy converter process when we consider the waste heat energy to the electrical energy. Okay. So, there are some other sources also from which the waste heat is seen. Even when a biological system, I discussed in the lecture, that when suppose a human being runs, they produce heat and this heat is getting lost. So, somehow if we can use this heat, one can also make a small device. Okay. So, I discussed this in the application, but these are the big the sources from where the heat is generated and they are also getting wasted. Some heat is of course is under use, but most of them are getting wasted and we have to convert them to electrical energy by thermoelectric generator. This is the main objective of thermoelectric generator based on thermoelectricity. Okay. So, the next question is, what are the basic difference between Seebeck effect, Peltier effect and Thomson effect? So, it is a very fundamental question, and going back to the discoveries of Seebeck, Peltier and Thomson, what we have studied is that whenever we consider Seebeck effect, we actually consider a thermocouple. That means, two the metals are connected, made a couple, and there are two the junctions. Okay. So, one junction if we put and hot and another junction if we make cold. Okay. So, then there is a temperature difference. Okay. So, if the hot junction temperature is T H is the temperature of hot junction, and T C is the temperature of cold junction, then we get an EMF which is proportional to T H minus T C or equal to Okay. So, this is thermo EMF, this is Seebeck coefficient. All right. So, that means when we talk about Seebeck effect, we have to make a temperature difference, and because of temperature difference an EMF is produced. But when we talk about Peltier effect, okay, the Peltier effect is exactly opposite. We use a thermocouple here also and pass current through this. That means, we create a potential difference between the two junction. Once we create the potential difference between the two junction, the actually the heat difference is created in the two junction, okay, depending upon the flow of current or the potential difference that is being created in the two junction. But in case of Thomson effect, we do not make a junction, there is a uniform the conductor where a current can flow following a temperature gradient. Okay. So, these are three important thermoelectric effects which we have studied from the basic physics, and out of this we have extensively used Seebeck effect in order to understand or design thermoelectric generator. Okay. So, let me come to the next question, why thermo EMF is generated when two dissimilar metallic junction are kept at two different temperature. So, why this EMF is produced I discussed in the lecture, but let me again summarize the points which I have discussed during the lecture. Why an EMF is produced? Because we know that for every metal electrons are filled up to a level which is known as Fermi level. Okay. So, it is this Fermi level of a metal, this is based on the free electron model, and these are all filled and this is above this, it is empty. But this is only at 0 Kelvin. Okay. So, if I look at the density, electron density versus energy, then there is a sharp drop here which actually decides the occupation of electrons in a metal, and that is at 0 Kelvin. Okay. So, if I look at the density of state of electron, the density of state of electron here is full and the density of state of electron beyond the Fermi level is 0. Okay. So, now if we increase the temperature, then slowly what we will see, the state beyond Fermi level starts filled up at finite temperature. So, we have density of state above Fermi level. So, if I connect, and this actually depends on which metal we are considering. Okay. If we look at the free electron model of the of metals, then we see that how to define the Fermi energy and how for different metals Fermi energies are different, and when we raise temperature, then how the density of state of electron changes and varies in metal to metal. Okay. So, if I have two dissimilar metals and suppose one junction is in hot and another junction is cold, and one metal say the density of state is higher at higher temperature, that is the Fermi level, above, beyond Fermi level or above Fermi level, we have density of states of electron, and in another case it is not that. Okay. There is a little enhancement in the electron beyond Fermi level, but not that much. So, there is an imbalance. As soon as we create a temperature difference, electron starts flowing from one density of state region, I can say now, to lower density of state region, and then when electron flows, an EMF is generated to balance the motion. Okay. And that is the reason why thermo EMF is produced. Okay. So, the thermo EMF actually depends very strongly on the density of state of electron, and therefore, it also depends on the concentration of electron, okay, and therefore, it depends on the very nature of the metal which are being used for a particular thermocouple. Okay. So, now let us look at the next question. Out of three materials, metal, semiconductor and insulators, why semiconductors are better thermoelectric materials? So, I discussed in detail about different materials which are being used in thermoelectric generator. But if we broadly classify the materials like metal, semiconductor and insulator, and then we have to choose which one in the broad classification of material, which one is a better material for thermoelectric generator. So, what is the quantities that we need to look at? The first thing which we need to look at is the figure of merit. So, how we have defined the figure of merit? Figure of merit is defined as where S is the Seebeck coefficient, sigma is the electrical conductivity, K or kappa is the thermal conductivity, okay. So, we have to look at this particular quantity, that means ZT or figure of merit. Okay. So, in order to increase ZT, we have to have higher Seebeck coefficient. Seebeck coefficient should be high, electrical conductivity should be high, okay, and thermal conductivity should be low. And we know that the thermal conductivity is basically, it consists of two components. That means, one is electronic part of thermal conductivity Ka or kappa, Ke or kappa E, and another is the lattice or phononic part of thermal conductivity Kl. Okay. So, now if we look at this three material, okay. So, first if I look at metal, in case of metal, Seebeck coefficient is generally low or very low. Electrical conductivity is very high and thermal conductivity is also very high. So, overall it seems that it does not give a very good figure of merit, because the figure of merit depends on S square. Okay, as Seebeck coefficient is quite low in case of metal, the overall ZT is low, and Seebeck coefficient is low because the charge carrier density is high in case of metal, and charge carrier density, okay, or electron density here is it is inversely proportional. Seebeck coefficient is inversely proportional to electronic charge density, and therefore, the Seebeck coefficient is very low in case of metal. In case of insulator, it is opposite. Seebeck coefficient is very high because the charge carrier density is very low, but sigma is very low and thermal conductivity is also very low. Now, if we come to semiconductor, okay, Seebeck coefficient is high, okay, or you can say moderate. Electrical conductivity is also higher as compared to insulator, and thermal conductivity is also higher as compared to insulator. Seebeck coefficient is lower as compared to insulator, but higher as compared to metal. So, it seems that there is a good optimization which one can do in case of semiconductor. Okay. So, if we look at the all the thermocouple and the temperature sensor which are being used, or in application of thermocouple which was discovered by Seebeck long back, they are all metallic. Okay. These are regularly used in the laboratory, okay, temperature sensor based on thermocouple. But when you come to thermoelectric generator, because of the figure of merit, which is the most important quantity to decide the final efficiency or power output of a thermoelectric generator, one has to see a best optimization of these three quantities. That means, Seebeck coefficient, electrical conductivity and thermal conductivity, and it seems that insulator is sorry semiconductors are the best choice. Okay. So, let me go to the next question. How semiconductor junction is used as a thermoelectric generator? So, once we have semiconductor, immediately we try to think how to improve the properties of a semiconductor. The best way to improve the properties of a semiconductor to have a controlled way of doping. So, when we dope, it becomes either p type semiconductor or n type semiconductor, and these are being used in the in electronics, and also we have seen the entire the solar cell which are based on p type and n type semiconductor. Here also again we have to make p type and n type semiconductor. So, this is an n type semiconductor, this is a p type semiconductor, this is hot end, this is cold end, and the circuit is made in this way. So, electron flows, how it is done? So, because of from the hot side electron flows to the cold side, because there is a gradient of electron concentration, okay, and it follows this path, current follows exactly in the opposite direction. Okay. And then in order to balance, again it is same as thermocouple, in order to balance its electron flow, and EMF is generated. Okay. So, there is a way one has to use the semiconductors for thermoelectricity or thermoelectric generator, okay, which is different from the design of metal. In metal, which we do, we just make two thermocouple, we just make a thermocouple, that means two junction of two dissimilar metals. And here, as we have discussed, the ZT is little bit different in the expression, different in that sense it now consider the Seebeck coefficient of both p side, Seebeck coefficient of n side, okay, and then resistivity or conductivity of n side, thermal conductivity of the n side or n type semiconductor, resistivity or electrical conductivity of p type semiconductor, and thermal conductivity of p type semiconductor. So, expression changes little bit, and this is the way one is to calculate the figure of merit when we consider a semiconductor junction in thermoelectric device. Okay. Now, the question is how power factor varies with charge carrier density. This is a very important question, because you know the charge carrier density controls a lot when we decide a particular material for thermoelectric generator. Okay. So, what is power factor? Power factor is electrical conductivity into Seebeck coefficient square. So, if we look at a typical plot, here we plot the charge carrier density, and here if we plot different quantities, okay, then what we will see that Seebeck coefficient actually reduces. So, suppose we plot Seebeck coefficient, electrical conductivity and power factor. Seebeck coefficient decreases because, as I told you, the Seebeck coefficient is inversely proportional to charge carrier density, and therefore, when you increase the charge carrier density, Seebeck coefficient decreases. So, we can see that this is typically, this is the metallic regime, and this is the semiconductor regime. This is metallic regime, this is semiconductor regime, and this is insulator. Okay. And then if we look at the power factor sigma s square, then it okay. So, this scale is actually a logarithmic scale. All right. So, this means that the sigma s square or power factor, it actually gets optimized in the semiconductor regime. That is what I had discussed in case of figure of merit also. And then after that the power factor decreases, and therefore, in general we have to choose a semiconducting material for thermoelectric generator. Now, let us see what are the materials that people have studied so far in order to make a good thermoelectric generator. So, the question is classify different materials used in thermoelectric energy generation. So, if we look at the study which people have made for thermoelectric energy generator, particularly the material scientist, it has started with chalcogenides. Okay. Bismuth telluride was the material which had started as a thermoelectric material, but these are all bulk form of materials. So, after that people have studied lot of bulk material like lead telluride, silicon germanide, which are used for different temperature regime. Like when we consider silicon germanide SiG, we use it at higher temperature. When we consider lead telluride, it is used in intermediate temperature. Okay. But now the question is there any other material which can be used in the bulk form as a good material for thermoelectric generator, and people have studied many materials and I have also discussed during the lecture. Okay. But apart from the bulk material, people have also started looking at low dimensional material, nanomaterial, nanostructured material, nanocomposites, okay, and then down to quantum material, quantum well, quantum wire, etc., in order to improve the property. Okay. So, we will just look at all these aspects, why different materials are being used and what is the reason for going to low dimensional material, what you can improve. But let us just see here that what are the materials that people have studied and what is the percentage of research. So, if you look at the chalcogenide, as I mentioned, this is the material which people have started working with. The chalcogenide had the maximum research work, almost 37%, doped semiconductor means 7%, hybrid materials are being studied around 7%, conducting polymers are also used and being studied, almost 4% research have been done, and then there are some miscellaneous material for 4%. Metal oxides are also being studied as a thermoelectric material, okay. And then people thought about if we can make a hybrid or composite, then how it is improved. Okay. So, almost 14%, and then coming to this nanostructure, which are also at times it is increasing. This is all the report which was in 2020, this particular paper, okay. And it has definitely the number has changed now with time. There is some gentle material 5%, half useful alloy 8%, clathrate around 1%, and scooterite approximately 7%. Okay. So, these are the materials which are being investigated by different material scientists in order to improve the the properties, particularly these three properties. The main thing is that either we have to improve or increase the value of Seebeck coefficient or the electrical conductivity and decrease the thermal conductivity. These are the main objectives of research, and at different times researchers have reported different materials with good or sometimes better properties. Now, what are the physical properties of phonon glass electron crystal? So, people thought that one ideal situation when we design a material, the ideal material would be phonon glass electron crystal, PGEC. So, what is the meaning of that? Its meaning is that as far as the thermal property is concerned, that means when we consider thermal conductivity, particularly thermal conductivity, it should behave like glass. Okay. That means extremely low thermal conductivity. All right. And when we consider the electrical conductivity or electrical property, particularly this electrical conductivity, it should behave like an electronic crystal with high conductivity. It seems to be contradictory. Contradictory in the sense when we consider free electron model, because in free electron model it is very clearly stated that the material whose electrical conductivity is higher, its thermal conductivity is also higher, okay, or electrical conductivity is lower, then thermal conductivity is also lower. But here we are in search of a material which is typically known as PGSC material, where thermal conductivity is very low and electrical conductivity is very high. The reason is that we want ZT to be high, electrical conductivity should be high, thermal conductivity should be low, and Seebeck coefficient also should be high, and this is the idea of PGSC material. So, it is not a very simple material. So, there are very complex structure, okay, material structure which can show close to PGSC material. They are crystalline structure, but you know that as we have discussed that there are some kind of vacancy in that structure, and in that vacancy there are something called the rattlers. Okay. So, what happens, these rattlers are actually phonon scatterer, alright. So, it does not they change the electrical conductivity of this material. It is perfectly crystalline structure for the motion of electron, therefore, it retains its higher electrical conductivity, but the scatter phonons, okay. So, and because of that the thermal conductivity is reduced. Okay. So, this is a good concept, PGSC is a good concept, and there are many materials which people have demonstrated as a good PGSC material, but the research is continued in this direction. Next, why nanophase material has a better potential as compared to bulk counterpart as TE material. So, I mentioned that after people have done lot of work with the bulk material, okay, still there are lot of work is going on in the bulk material, people started looking at, can nanomaterial helps in improving the efficiency of a thermoelectric generator, that means in improving the power factor or in improving the figure of merit. Okay. So, one thing which is important in case of nanomaterial is that because of the quantum confinement effect, there is an enhanced density of state, and this enhanced density of state or DOS eventually increases the Seebeck coefficient. This is required for a high figure of merit or higher power factor. So, it seems the nanomaterial has importance. Another which is extremely important for nanomaterial is that the reduction in the thermal conductivity. This is a very important thing, okay? Reduction in thermal conductivity. So, how it is done? Because in nanomaterial there are different interfaces, okay? There are small structures. So, because of that, if we consider the mean free path of electron and phonon, okay, the electron mean free path is long enough, so they are not getting disturbed by these structures generally. But phononic mean free path is such that there is higher scattering of phonons, which actually lead to lowering of thermal conductivity, particularly this phononic part of thermal conductivity. Okay. So, we know that the thermal conductivity consists of both electronic part and phononic part. The phononic part of of the thermal conductivity reduces when we reduce the dimension of the material or we go to nano dimension. Okay. And if we look at its bulk counterpart, if we retain all other quantities same, then we have a reduction in thermal conductivity which leads to enhancement in figure of merit. Additionally, we have enhancement of density of state which increases the Seebeck coefficient. So, it seems that nanophase material is a good promise when we consider it as a thermoelectric generator material. Okay. The next question is figure of merit of a nano composite is generally higher than their bulk ingots. Why? So, suppose bulk ingot means suppose I use a say bismuth telluride or lead telluride or make some composite nano composite structure. In one case we have bulk ingots, in another case we have nano composite. Okay. It has been observed that a nano composite gives a better figure of merit, and the main reason behind this is this reduction again in the thermal conductivity. Which actually causes enhancement in the figure of merit. Again the logic is same, because when we make a composite structure we have lot of interfaces, lot of inclusions in the structure, okay, which actually becomes a very good phonon scatterer. Okay. So, this is a very important thing, that this is the way the present research is going on, how to make inclusions in the material, nano inclusions in the material, so that the phonon scattering is high, okay, and then the phononic conductivity, thermal conductivity is reduced. So, this is a good way to control the the thermal conductivity of the material and reduce the thermal conductivity to enhance the figure of merit. So, nano composite is also another very interesting material class of materials which people are studying recent time in order to improve the efficiency of a thermoelectric generator based on nano composite materials. Okay. So, let me go to the next question. What are the basic components of a TEG module? Now, we come to a bit of device part. So, what the TEG module is, I have already discussed in the lecture. Let us again draw a small TEG module. Okay. So, this is TEG module where we have a p type semiconductor, we have a n type semiconductor. Okay. So, what is this? This is actually a heat exchanger, and this is also a heat exchanger. Okay. So, this is at say hot, higher temperature TH, and this is at lower temperature TC. Okay. And then we have a load connected outside. Okay. So, this is the current flow, electron flow is exactly opposite. Okay. So, this is the heat exchanger. So, this is the heat energy in, Q in, and this is Q out. So, okay, so when we talk about a TEG module, it actually consists of two things. One is the heat exchanger and another is the thermocouple. Okay. So, here you can see very clearly. So, there are heat exchanger and this is actually or the junction made up of semiconductor. Okay. So, the architecture is that the heat exchanger actually allows the heat to flow from this side and this is the flow of heat outside, and then we have a p type and n type semiconductor which is a junction, okay, semiconductor junction, and then a load is connected in the outer circuit maintaining the temperature Th at the hot junction and Tc and the cold junction, and the mechanism we know why there is a flow of electron and why there is a finally power output is taken across the load. Okay. So, we understand this a typical TEG module. Now, when we analyze a TEG module or a real thermoelectric device, we can make a little bit of small the circuit equivalent of that which is shown here. So, the question is draw schematic of a TEG circuit with temperature at hot junction Th. So, what I have drawn is a TEG module is now in the circuit form and a cold junction Tc, okay, and a load RL is connected, all right, with the circuit. What is the expression of current, power and efficiency? So, we discussed about it, but if again if you look at that we have these two the element thermoelectric element A and B, and this is the flow of heat, okay, and this is the current which is flowing across the load, all right. So, if we write the expression of current, it is nothing but the EMF which is being generated divided by the total resistance. So, total resistance, if I consider the resistance of the element thermoelectric element as R and load resistance is RL, then the total current is S delta delta T S into delta T. Delta T is the temperature difference, that is Th minus Tc, okay, divided by the total resistance R plus RL. Okay. So, how do we define power? Power is simply I square RL. Okay. This is a power which is getting delivered across a load. And how do we define efficiency? Efficiency is nothing but the heat energy that is being given and the power, and we have to look at that how much power is generated and how much heat energy is provided from the hot source to the thermoelectric junction. Okay. And then we have made a detailed calculation in the lecture, and I have shown what are the factors that an efficiency depends on. It efficiency critically depends on the temperature difference, okay, of the two junction, all right, and also the figure of merit ZT. So, we can either change the delta T value, that means the temperature difference between the two junction, or we change the value of figure of merit in order to obtain or in order to change the efficiency of a thermoelectric generator. Now, we come to a point that if we keep on changing the figure of merit, how this efficiency changes. So, there is a plot. So, the question is, in a case study TE device efficiency versus temperature is shown below, explain the graph. So, you look at this graph. So, graph this x axis is the temperature difference, y axis is the efficiency. So, I told you that efficiency critically depends on two quantities. One is temperature difference and another is ZT or the figure of merit, and this is very nicely demonstrated in this. So, if you look at for different figure of merit starting from 1 to 10. So, 1, 2, 3, 5, 10. So, you can see that the efficiency is higher when we consider higher ZT value or higher figure of merit, and lower when we have lower figure of merit. Okay. So, now if we look at the temperature difference, so suppose I am here at a temperature difference of say 600, it is lower than the temperature difference at 800 and higher than the efficiency is higher than when the temperature difference is 400. That means, when we increase the temperature difference, we have higher efficiency. But now, if we go from graph to graph, from this one to other one, then we see that there is a huge enhancement if I am only considering a particular temperature difference, which is 600, and you can see there is a huge enhancement. So, when I come to this point, the device efficiency is close to 15, and when I go to this point, the device efficiency is close to 40, more almost 3 times enhancement in the device efficiency, keeping the temperature difference same, but changing the figure of merit value. Okay. So, this is what we learned from this particular exercise, and then we come to more low dimensional material, as I mentioned, that quantum well. Okay. So, the question is, a silicon germanide quantum well structure is shown below. Okay. Why this is considered as good thermoelectric material? So, you can see this how the quantum well is formed, that is what I discussed in the lecture also. This is silicon, okay, and this is silicon germanide, and the dimension is extremely small, 100 angstrom, 100 angstrom, 100 angstrom, it is because only 10 nanometer, and the small the layered structure or well is formed in between. Okay. So, sometimes people also call it as a strained layer, or sometimes if we repeat this particular structure, we call it superlattice also. So, this is a very interesting material for thermoelectric generator, and why it is better, because now if we look at the density of state. So, this is the density of state of a bulk material, this is the density of state of 2D material, this is the density of state of 1D material, and this is density of state of. So, I can write the density of state for 3D, 2D, 1D and 0D. So, now if I consider the density of state and make a difference between 3D and 2D, what we see that density of state is an asymmetry, okay, close to Fermi level, and therefore, there is an enhanced density of state, which leads to enhanced Seebeck coefficient, or also quantum confinement effect gives us higher density of state and higher Seebeck coefficient. Okay. Another interesting property is that we can get higher sigma. So, ZT becomes higher. Now, we can have higher sigma, okay, again because of quantum confinement effect. The electrons are properly channeled only across the or through the quantum well. Okay. There is something called modulation doping, where ionized dopants are used. Okay. These ionized dopants are used to increase the electron density, but the ionized dopant stays in the boundary of the well, and electron flows only inside the well, and therefore, their motion is not hindered by the presence of ionized dopants which are close to the well. So, which are at higher energy and the quantum well at lower energy. So, electrons motion is not restricted, eventually increasing the electrical conductivity and enhancing the ZT. Another is that we can also have a situation like reduction in thermal conductivity, because I told you that these are strained layer, very thin layer of silicon, another thin layer of silicon, and then one thin layer of silicon germanide, and then if you repeat this structure it is completely strained layer, and because of these interfaces, okay, there is an enhancement in phonon scattering again, which leads to reduction in the thermal conductivity and enhancement in ZT. One can also have very small nanoparticle inclusion in the well. Okay. That is a very good situation, and which actually leads to further scattering of the phonons, leading to more reduction in the thermal conductivity and enhancement in the figure of merit. Okay. And therefore, it is a good material, because just now we have seen, if we have a higher figure of merit, we have a higher efficiency. Now, we come to the last part of this these questions, and this is related to the device output when we make a device. So, what is the power output? So, the question is power density versus temperature of TEG device made up of different materials are shown below. Explain the result. So, if we look at this particular the graphical study, this is the temperature difference along x axis, and this is power density along y axis. Okay. And now, let me consider again the temperature difference. So, you look at this expression for power. So, expression for power critically depends on this power factor alpha square sigma. Alpha is again Seebeck coefficient. Okay. So, power is proportional to alpha square sigma or S square sigma. Alpha or S both are these symbols of Seebeck coefficient, and also it is proportional to delta T. Okay. So, again if I am in a particular material, say looking at silicon germanide, which is this one, for a delta T 200, okay, and for same silicon germanide, if I look at the power at say 300, there is an enhancement in power because delta T is enhanced. But now, if I go from one material to another material, from SiG to, if I consider BiT, where we have higher ZT, then there is a further enhancement of the power delivered. Okay. So, in terms of the final device performance, it is extremely important that we optimize the two things, that is the temperature difference and the figure of merit. Okay. Another point is that, as you remember that in the lecture I discussed that when we make a real thermoelectric generator, we have different legs of PN, 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 etc. of the junctions. Okay. So, it also depends on number of legs we use, proportional to number of legs, and also it is proportional to area. You can see it is proportional to area. So, these are the few things which we have to look at while we design a particular thermoelectric generator based on large number of PN junction thermoelectric legs, okay, and optimize the power for different ZT and delta T values. Okay. So, let me quickly review this chapter with some frequently asked questions. So, the first question is, why thermo EMF is generated when two semiconductor junctions are kept at two different temperatures. So, I discussed that when we kept two junctions at two different temperature, there is a flow of electron from n side to p side, okay, following the concentration gradient, and then in order to the balance this electron flow, a thermo EMF is generated in the junction. Second question, how thermo EMF varies with temperature in a thermocouple. So, we know this is a very fundamental question, and what we have seen from the basic study of Seebeck, that the thermo EMF is basically, it is equal to Seebeck coefficient into temperature difference, okay. And this also varies with temperature. So, if we plot thermo EMF versus temperature, this is a typical parabolic plot. Okay. So, this is the way the thermo EMF varies with temperature, and which is from the very basic theory of thermoelectricity. So, the third question is, what is the role of Fermi level of a material in thermoelectricity? So, I discussed very clearly that when we design a thermocouple, we have to look into this aspect. When I consider two dissimilar materials, we have to look at it where their Fermi energies lie. Okay. So, if Fermi energy is higher for one metal and lower for another metal, it is always good, and there is a easy flow of electron following the temperature difference, and which is compensated by the thermo EMF generated. So, this is the importance of Fermi energy or Fermi level in thermoelectricity. Why semiconductors are better material for TEG as compared to metals and insulators? So, that also I discussed, because the semiconductor, these values are moderate. Okay. The charge carrier density is moderate. So, we have a higher Seebeck coefficient as compared to metal, but lower Seebeck coefficient of course as compared to insulator. In terms of electrical conductivity, insulator electrical conductivity values are in between metal and semiconductor, and thermal conductivity is also same. So, all these quantities are moderate or in the optimized proportion, and I showed you that when you plot the charge carrier density versus the power factor, there is a optimized point which actually lies with semiconductor, and therefore, the semiconductor are the better material for thermoelectric generator. Why it is important to reduce thermal conductivity while designing a thermoelectric material? So, I told you that these days a lot of research effort is going on in reducing the thermal conductivity, because the figure of merit is inversely proportional to the thermal conductivity. If we do not have much option to change the Seebeck coefficient or electrical conductivity, we can reduce the thermal conductivity by making the structural change of the material, enhancing the phonon scattering, reducing the thermal conductivity, and improving the figure of merit value. So, next question is, why nanomaterials play an important role as a material for thermoelectric energy? The reason behind this is that because of the nanomaterial, as I told you, that we reduce the dimension. So, when the dimension is reduced, the density of state is higher. So, when density of state is higher, we have higher Seebeck coefficient. This is one part, but another which is very important part is that reduction in thermal conductivity because of enhanced scattering of phonons. Okay. What are the advantages of a TEG device? Okay. So, we know there are many energy devices, and in future I will also discuss about other energy devices like batteries, okay, fuel cells, supercapacitors, etc. But one of the important thing with TEG device is that it is all solid state device. This is a very important thing. Its stability is very good. Okay. The second thing, the third thing is that it does not have all the harmful the output which we have in many other batteries and other thing. Okay. And it is the one in that sense, it is a power generating device which is a green power source. We can say that if we do not use any material which is toxic, and it is possible. Okay. And then of course, it is a miniaturized device. Okay. As I have discussed during lecture, then one can put a small thermoelectric device in the shard, and then it can generate little bit of power, and people have also seen that in a heart, when they use pacemaker, the thermoelectric devices can be used, or in the shuttle, a space shuttle, where we do not have much space to put a big energy generating device or the energy storage device. Thermoelectric generator can be nicely placed, which can generate little bit of energy and which is required for this space shuttle. Okay. So, these are some advantages of using thermoelectric generator, and of course, thermoelectric generator are not the energy producing device which can use for large scale. It is only for portable uses, okay, or the small scale application. Okay. Question 8 is define maximum efficiency of a TEG in order to improve TEG efficiency. What are the factors one should look at and how they can be modified? So, as I told you that the efficiency of a TEG, it depends on two things. One is the temperature difference and another is the figure of merit. So, maximum efficiency is nothing but what is known as Carnot efficiency. Okay. And if we make a percentage, this is a percentage. Okay. Let me just. Okay. So, this is the maximum efficiency, but you know that it does not work with the maximum efficiency. Efficiency is greatly reduced because of many other factors, but of course, one can enhance efficiency, and at least by choosing a proper figure of merit, okay, or the enhancing figure of merit. I have shown that efficiency can go up to the 40-45%, which is very good, although it is still now it is far to achieve, but one can theoretically think that, and also experimentally people are trying to demonstrate higher efficiency. All right. A quantum well Bi2Te3Teg has much higher efficiency as compared to the bulk counterpart. Why? So, I already discussed that when we make a quantum well structure, 2D quantum well structure, the density of state is higher because density of state distribution is asymmetric, close to Fermi level. So, because of higher density of state, there is higher Seebeck coefficient, this is one point. Second is the electrical conductivity is higher because the charges flow only in the well, okay, and because of modulation doping, one can also enhance the electrical conductivity, and thermal conductivity is lower because they are strained layers. So, therefore, there is a higher phononic scattering which leads to lower thermal conductivity. So, all these three properties seems are good, nicely optimized in case of quantum well, eventually enhancing the efficiency or the performance of a device. The last question is what are the critical parameters of T power generator? So, thermoelectric power generator, the critical parameters, the most important parameters which we have seen that when we design a thermoelectric generator. Okay. So, the most important thing is that the power factor, which is S squared sigma. Second is the temperature difference delta T, and also it depends on number of legs, how many legs we are using, p-n junction leg, and also area of the legs. So, once we optimize all these quantity, we can optimize the power, and I have also shown you one particular case study where people have shown at least how the variation of delta T and the figure of merit can lead to higher power output. Okay.